Hello, this next video in a playlist that I'm calling General Linear Models Design of Experiments, and within this playlist I create little mini-series that are based upon the different types of experimental designs. This one we're doing a balanced two-factor factorial design without interaction. This is part 3 of a 7-part series, and we're looking at partitioning the sum of squares. Now, as a reminder, the model is y equals x beta plus epsilon, so it is a linear model. Then the design matrix can be partitioned into the two, a 1x alpha, which deals with factor A, and x beta, which deals with factor B. And then these are the parameters associated with it. And I'm going to point you back to parts 1 and 2 of this little mini series for more detail. Epsilon, of course, is normally distributed, mean vector 0, covariance matrix sigma squared I. Now, partitioning the total sum of squares, I think is easiest to do it in matrix form. So the sum of squares total in matrix form is y transpose I minus j times y, where j is the perpendicular projection matrix onto the column space of ones defined like this. And this creates a matrix. U is a matrix of all ones. And if the index down here indicates how many rows, and if this is left off, then it's how many columns too. So it's a square matrix of 1 over a times b times n. Now, if we add 0 to this, we don't change it. So we subtract and add m, where m is the perpendicular projection matrix onto this column space, x star. Now we can think of it as in groups, so I minus m will come down here and mj will come down here, when you multiply the y's in. Now, whenever you see I minus m, so it's y transpose I minus my, that is always the sum of squares there. So we're done, we've just partitioned it. Now this piece, we write in what we know about the perpendicular projection matrix onto the column space of x star. And that is m alpha, m beta minus j, where those are the perpendicular projection matrix onto the column space of x alpha and x beta respectively. Now, and we can also expand m into what it is here. And this will help us understand like the scalar notation for the sum of squares there in this design. So now here we take this I minus j and keep it with this one, but this I minus j we put it with this alpha, and then we can rewrite them like this, and that's it. This is the sum of squares for treatment A, sum of squares for treatment B, or factor A, factor B. Of course, this is the sum of squares there. Now, as a reminder, the perpendicular projection matrices onto the column space of x alpha is this, and its form is block diagonal and then 1 over bn, and this is a matrix of all ones, so that's multiplied in. So block diagonal, so it's a block diagonal of bn, and it goes down the matrix diagonally of just a chunk of those, of the 1 over bn. Now the perpendicular projection matrix onto the column space of x beta is defined like this, and it is this. And even though I tell you what it is, I write it out so you understand it. So it's a block diagonal of 1 over an, but then it's a block diagonal. So the whole matrix consists of this going across. Each little block is a block diagonal. And this is A by A blocks. So there's A big blocks going this way, A big blocks going this way, and then within a big block it's block diagonal of 1 over an. So now let's look at when we multiply y times j. Now remember, j can be thought of as this. It's a vector or a matrix of all ones and then times 1 over abn. So when this first row is multiplied by this, it adds up every y element. So it's the sum. But then you divide by that and you get the mean of all the y's. And you do that for each row. Each row is just a row of all ones. So you get a one vector times this sample mean, or the grand mean is more appropriate. So we represent it by YGM. And again, the grand mean, a dot means sum over that index, and then Y means divide by how many things you've summed. And so the grand mean can be thought of as this, the sum of I, J, K. Now, Y times the perpendicular projection matrix on the column space of X beta is this. So this is block diagonal Y. Now, if we think about this, remember this is block diagonal. So the first chunk has Bn ones and then the rest zeros. That's that first row. So when you take it times this, you're picking off only the y's that pertain to the level 1 of factor A. And then each row is the same. So you're going to get like a one vector times this treatment 1 mean. And then when you go down to the next block, the row is zeros, all ones, zeros. So when you do that matrix multiplication, you're only picking off the y, the response, or the y variables that correspond to the level 2 of treatment A. And so you get this vector of quantities, and we call that the mean vector for treatment A. And if you think about this, this is the perpendicular projection matrix onto the column space of X beta. So whenever you pre-multiply some y or some vector times it, it's going to shove it into the column space of X alpha. And that's exactly what this is. X alpha consists of, remember it's ones that go down the diagonal. And so it has to be in that column space. So it's a column, some constant times this, some constant times this, some constant times this. Well, it turns out when y is the vector we're multiplying by m alpha, then it creates the level means, the factor level means for factor A. And for m beta y, remember it's a block diagonal, and so this is going to, there's A in ones, but it's block diagonal, so it's picking off, then there's ones, then not ones, then ones, and because it's this block, is across. Anyway, it creates what's called the treatment mean, the mean treatment B vector. And so here, this is the mean for response 1, or level 1 of factor B, level 2 of factor B, the mean, and then of course it's constant or one vector. And then this repeats all the way down. It's repeated A times. And then that's the format of this vector. Now let's convert all these sums of squares to scalars, because that's what you see in most books. And we're kind of following a book by Douglas Montgomery titled Design and Analysis of Experiments, and he puts everything in scalar form. So if this is the sum of squares total, then this is idempotent, so you can take it times itself, so there's two of them, and then this second half you can sort of untranspose it and you get this. Now let's multiply the y vector in, and this is just a vector product, and so you're going to get a bunch of squared things, which is this. Now for the sum of squares for factor A, this was the sum of squares. So remember, this is an idempotent matrix, so you can have two of them. Then you kind of untranspose the left side, multiply the y in, and you get this y, the mean vector for factor A, and the grand mean. So this is a vector product, and you're going to get squared things. But notice that there's no index for j or k in this, so you're going to get a lot of repeats. And so when this is multiplied out, that's why you get B and N. So that's like the J index and that's the K index. And so this sum is squared. Now, for the sum of squares for factor B, remember that's an idempotent matrix. Multiply it, sort of untranspose it, and you get this. Multiply the y vector in, and you get this. Notice there's no index for I or k, so you're going to get a lot of repeats over those, and that would be this. That's why there's an an out front, and then that's the sum of these squares. So that's the sum of squares for factor A. And these are all what you see in books. And so the sum of squares for air is this. That's idempotent, so you multiply it and you untranspose it and you multiply the y in and you get this. So when you multiply this out, you get this. So each one, this has an IJK index, so we're going to need all three sums. Anyway, when this is multiplied out, you get this triple sum. Okay, well that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.